All right, good afternoon. Let's get started. Good. So last couple of lectures, we talk about in a beam, how do you find the shear force and the bending moment, right? So we basically draw a VM diagram, and then you find out where the maximum is. So you figure out where the load is maximum in a beam, right? So we need to able to do it for 3 type of beams: simple beam, cantilever beam, and overhanging beam. And for all 3 type of load: country force, country movement, or distributed load. Right. So we have homework there for you to practice and try it. If you have questions, come over during my office hours. I can help. All right. So just a quick review here, or quick test here for you. So if you have this one simple beam, there are 2 loads P applying there. Is this VM diagram correct? Yes, right? So the 2 load P there, so the 2 reactions will be equal to P. And therefore, the shear force jump up with P, and then go until you see this constant load jumping down P, and then 0. Right? So we actually had this result before. Okay, so we talk about this situation, we call it a 4-point bending. And 4-point bending, that is basically a pure bending in the middle part. Because in the middle portion, right, you can see there's no shear, only bending moment. Okay. So today we're going to, based on this pure bending situation, we're going to describe how can we find out if you apply a bending to a beam, what's the stress in the beam, and what's the deformation of a beam. Right? And this chapter, chapter 5, actually focus on stress. And then later on, we have chapter 9, and going to look at the deformation. Right? That's another chapter. So each part is actually a chapter. But basically, it's a different part. Right? Okay, so for today, we're going to talk about stress in a beam. And that is determining the kind of stress in the beam. As we know, internally, if you cut a beam, you're going to have 2 internal reactions. One is the shear force, right, V. Another is a bending moment. So in general, you're going to have 2 types of stress. One is the shear stress, one is the what we call bending stress or normal stress. Okay, so we'll start with the easy one, that is the bending stress, the normal stress. Okay, so we talk about the situation when you have a pure bending, only a pair of moment applying here. All right. So to be able to get the deformation, here we come up with another called plane assumption. Okay, so what's the plane assumption? All right. So before I mention, I'll give you some of the samples I have here. So you do the spending, then say what you observe. All right. So this time I have quite a few. Right. So I can throw you. All right. Okay. Okay, 3 more. Here. Okay, give this back to me, all right? So the front, you can read this one. All right? Okay, now bend it. See, imagine you are bending a pair movement here, right? A pair of force, right? 2 fingers, that's a pair of force, movement. So it's pure bending. Now, bend it, and now look at this, the lines there. Okay, see, if you say any plane that remains as plane, any plane assumption, right? Okay, first you can cut the plane like this. Right now when you bend it, the plane remains plane or not? No, the bending, right? Curve. Now any plane remains as a plane. The vertical one, right? So the cross sections, that's a plane. Initially you see the straight line, I draw there pretty good straight lines, right? Now if you bend it, okay, bend a little bit, you see the line still straight? Okay, so that's imagine it's basically a plane, right? When you cut cross sections. So this plane here will remain as a plane when you bend it. So that's the plane assumption. All right. So it's like a accordion here, right? I found this picture from internet. So it's like when you move it around, right? It's basically all this plane remain as rigid plane. That's how things deform as a beam. Okay, so is that easy to accept as a plane? Right? Okay, so this is the fundamental assumption we're making. So we'll determine the deformation and the stress based on this assumption. Right? So all the plane, if you look at it here, they will rotate, right, relative to each other, but they will remain as a plane. All right. Okay, so now first let's clarify one concept about positive deformation or negative deformation. Okay, so we mentioned this earlier. We define a load, a moment, positive and negative, based on deformation. Right? In this class, we always do that. If you have a pair of force, stretch it, and elongation, that's a positive pair of force, and that's a positive deformation. Okay. Similarly here, if you have a pair of moment that makes this thing bending upward, we call that a positive bending. Right? So the deformation is positive, and that pair of moment is positive. So that's how we define positive and negative. Right? Okay, so now let's go look at this. If you have a beam, imagine this is a beam, part of the beam, right? Have a very long beam. Now you just look at the portion of it. Okay, we need to find out how it deforms. Okay, so here is a verbal definition of what's a plane assumption. You can read the textbook. So I'll just skip this one. All right. Okay, so now look at this, the model, the sample you have there. Okay. Now I want you to look at the one line. I draw a line in the middle. Okay. Now when you bend it, can you kind of judge whether that line gets elongated or shrinked? The one in the middle. Okay. If you look at the tip, top, if you bend this way, okay. What about the line here? This part gets longer, right? This portion, this one, the bottom edge gets shorter, right? If you do the other way, if you bend this way, this line gets longer, the other one gets compressed, shorter. Okay, one part gets longer, one part gets shorter. Can you imagine must be somewhere in the middle? That's neither elongation nor compression, right? So that plane, we call it a neutral axis, because it's neutral. That means no elongation, no shrinkage, right? So there must be one there. Actually, if you look at the form I gave to you, the one in the middle, actually, that's that. Because you can see, actually, I have this one, all draw small blocks. So when you see here, when I bend it, so you can see all this get crowded together, and this are kind of separate apart, right? So that tells us there's one line in the middle, neither elongation nor shrinkage. So we call this one neutral axis, all right? Okay, now with that, we can actually figure out how things deform. I mean, how much deformation and then how much the stress. Okay. Okay. Before that, first, why we need this plane assumption? Why we need based on the plane assumption to look at the stress? Can we somehow say the stress in this beam is uniform? Then you average something, say a force divided by area. Can you do that way? The answer is no. Okay, why is no? Is this thing deformed uniformly? If you look at here, okay, all on the cross section, top to bottom, are the deformation uniform? I mean, same deformation everywhere. Is that true or not? No, because you see here, this part gets compression. It's a negative value. Here is a positive value, elongation. So it's not uniform. Because it's not uniform, therefore you cannot just use force divided by area, get something average. So therefore you have to base on deformation. That's what we did in chapter 3, right? Remember we had a plane assumption because it's not uniform. Okay, for same reason, here we need the plane assumption for not uniform. Okay, so all right, so now let's look at this pattern, how things deform, and then figure out what's the strain, the deformation strain, and then you can strain times Young's model to give you stress, right? So therefore we can get stress through deformation. Or in other words, you do deformation analysis first, then you figure out the stress. Okay, so here is our analysis. All right. So imagine you have a long beam it's under pure bending, so you apply a pair moment, bending positively, right? Positive, so upward. All right, now to find out the stress, I have to use a plain assumption, say how things deform. And to do that, same trick. We'll cut a small block out, right? Look at that block, how it deforms. That's the same trick we already used twice already, the previous definition, right? For the bar, for the shaft, we use it. Now for the beam, we're going to use it again. All right, so let's say we cut off a small, tiny element, dx, right? That's right there in the middle. Okay, so that's this part, this portion. So this is the dx. All right. Now, if we look at this block, when you bend it, how would it deform? And the bottom actually draw how would it deform. Okay. So the top somehow get closer, the bottom get far away. So you have this kind of definition. This plane is like this, my two arms like a two plane, right? Originally parallel, now deformation, so you just turn this way. Now, right? So this part get closer, this elbow part get far away. Okay. Now, can you determine how much strain you generate at any location? For example, MP location for this part. This part, can you determine the deformation? I mean the strain. This line gets shrink, right? Or this line gets elongated, negative value. How do you determine the strain? That's the goal we're trying to achieve here. We want to find out the strain. Why we need to find the strain? Because if I know strain, then I can multiply E, I get stress. Right? So I need to find out strain. For any arbitrary location, like I show here, this point here, location is Y from the neutral axis. Because the neutral axis, that's where I know there's no deformation. It's initially straight line, just curve. There's no stretch or compression. They remain the same. That's why we call neutral axis, right? So the neutral axis is that's the SS curve there. All right. Now let's say a location of distance y from that location, from the neutral axis. Okay. So the EF. Okay. I want to find out how much this EF deform when I bend it, or how much is the strain there in line EF. How do you calculate the strain in line EF? That's my question. How do you calculate strain in a line? Should be the final length minus the initial length, then divide the initial length. That's what we learned back in chapter 1, right? Okay, so therefore our task is find out what's the final length, what's the initial length, and then you calculate the ratio. All right, now if I cut the element, initially I cut here, right? So straight one, so the top one. I cut the dx, this element is dx. Now what's the length of the EF in this figure? What's this length here? Is that dx? Let's say rectangular, you cut a parallel surface, right? So dx is everywhere. So EF initially is dx. Now, what is this after deformation? What's this one? What's the arc length? So this arc length, okay, we call it ds. I'll just write here. Okay, this ds should equal to what? Equal to this distance. We call it rho minus y. That's the radius of curvature. When you bend it, right, there is a radius curvature. It's a rho minus y. Because rho is referred to the neutral axis. You see there where this rho referred to here. So you minus y. So therefore the radius will be rho minus y. Okay, so this is the radius. Now, this angle, let's say this angle here is d theta. Now, what's this arc length? What's the arc length of angle d theta? Right, so this will be times d theta here, right? D theta times the radius, that gives you the arc length. Okay, you will say, what's d theta? Oh, we'll find out next. But it's supposed to be d theta times the arc length. I mean the radius of curvature, right? Okay, so that's the ds. Initially was dx. So the change should be ds minus dx, right? Okay, so that's what we have here. See, the string is the final length minus the initial length, then over the initial length. Okay, so now what's the final length minus initial length? EF prime minus EF should be ds minus dx, right? Is that clear? ds minus dx. Okay, now what's ds minus dx? Oh, what's dx? Is dx, I draw here, is dx equals to rho times d theta? Is that true? Based on which picture? Based on bottom one, right? See here, you call this radius rho, right? So therefore, this distance ds is equal to dx, because this y ds equal to dx here. Because it's neutral axis, there's no definition there, right? So for this line here, this ds here, we call ds neutral, is equal to dx. And this ds neutral equal to dx. And that's supposed to be equal to rho times d theta. Okay, so with that, now you can take it, combine those equations. Okay, combine these equations. What do you get? So ds dx equals to what? Negative y d theta. Because the first term, they cancel out. Rho d theta, right? Cancel out. Okay, so now the length change is y d theta, right? Divide the initial one. So let me write one more step here. So this will be, the difference will be rho y d theta. Okay, negative. Then the bottom will be rho d theta. Therefore, you eliminate d theta, you get this one. Right? Okay, that's our all geometric relation. Okay, any questions here? You all agree this, right? Radius length equal to the radius times the d theta, right? That's something very basic. Okay, so with that relation, we have this equation now. So the string at location y, this at location y, is equal to y over rho. Because, oh, what's rho? Okay, we'll find out later. But let's say you have this rho, then the string will be y over rho. You all agree? Follow? Okay, if you all agree, follow, then we'll move on. Next, we can see what's there. Okay, so now summarize what we just get. Okay, so the string at location y is y over rho. All right. So how does the string change in a cross section of a beam? It's linearly proportional to y. Right? So when y equals 0, the string is 0. Where is y equals 0? Middle, the neutral axis here. The neutral axis, right? So this is the neutral plane or neutral axis. That's where string is 0. That's neutral. That's easy to follow. Okay. Now where the string is maximum? Wherever the y is maximum. So it will be either this part, where it further away from the neutral axis, or it can be this part, depending on where your neutral axis is located, right? In this figure here, it actually should be in the top because the distance in the top is bigger. Right? Yes?
How do you not have the neutral axis in the middle?
Well, good question. Why you don't have it in the middle? Okay. It will be in the middle if you see the rectangular form I just gave to you. But in general, it may be not. So let's say you have a beam is triangle. Cross-section is a triangle. Then it's not symmetric. So it will be somewhere 1/3 of this. So in general, it's somewhere. Okay, we'll find out where. But for now, we'll say there's somewhere in between these two edges, there must be a neutral axis. We'll just randomly put a location. Right. Okay, so we have this relation. Now, with this strain, we can calculate stress. Okay, that will show here. Stress is just strain times Young's modulus. Now, so you have stress equal this. Okay, now what kind of distribution do you have for stress? When you look at the cross-section of a beam, it will be 0 in the middle when y equals 0. And then biggest either the top tip or the bottom tip. Right? So strain stress, they are the same distribution, it's linear. It's a line, linear, right? Straight line distribution. All right. Okay, so that's the basic equation for strain and stress. All right. But we haven't finished yet because we don't know rho yet. If I apply moment m, right? So I know I apply moment m. I know the beam, what's the size of the beam. Okay, how can I find out what's the stress? I need to find the rho. Now, how can I find the rho? How is the rho related to the moment I apply there? Okay, rho will relate to stress, as shown here, right? How is stress related to the moment? Right? If you have like this one, like this distribution here, right? You have the stress distributed this way. Now, what's the moment here, m here? If you have this kind of stress distribution, can you calculate the moment? Okay, let me change the question. Where you get the stress? This kind of distribution, where you get the stress? Why this beam generates the stress? Because you apply moment, right? Bending moment. So you have a stress. If you don't apply any moment, there will be no stress. It will be all 0, right? So the stress of this distribution comes from the moment, right? It comes from this moment. Okay, now this stress comes from the moment. Okay, now let me change the question. This stress, if you add all this together, what is the total effect? Resultant. What's the resultant of this stress? The moment. Why? Because this comes from the moment. There's no force applied there. So therefore, when you add them together, there should be no force, only a moment. Because otherwise, with strain, there will be a force applied there. And we said, no, this is pure bending, only movement. Right? Okay, with this understanding, next will just mathematically easier. So the stress, if you integrate them together, calculate the moment should equal to the m. Okay, so therefore we can find out the relation. Okay, here is the mathematical part. So the stress is given here, right? This equation. Now, we can calculate the total force generated by this stress. That's the calculation here. So you can add all the stress, small, tiny forces together, and that should be 0, because there's no actual force. The n equals 0. So you have this relation, and that gives you this relation. And that's the equation we can use to determine where the neutral axis is. Right? Okay, this equation looks familiar. We learned that in statics. That's the centroid. When you have this, right, equation equals 0, that means this point is the centroid. Okay, in other words, this equation shows that the neutral axis has to pass through the centroid of the cross-section. Okay, what's the centroid of a shape? For example, a circle. Where is the centroid of the circle? The center. Okay, where is the centroid of a square? Okay, if I have a square, it's right in the middle. That's the centroid, right? If I have a rectangular, where is the centroid? It will be here, middle. So the neutral axis must pass this point. The neutral axis must pass this point. And for a circle, this point. So the neutral axis must pass this point. That's where the neutral axis is located. Now, what about triangle? You get vertical line, right? Then 1/3 from the bottom, or 2/3 from the top. That's the centroid. And therefore, the neutral axis will pass this point. That's the neutral axis. Okay. So this one just tells us there must be the neutral axis pass through the centroid. And so now we know where the neutral axis should be for a given shape. Right? Okay, so next, let's find out the moment. Okay, so I'm just copy the stress equation here again. Okay, now how do you calculate the moment generated by the stress sigma? Should be the stress times the area. That's dA, right? That gives you force. If you look at this location here, say you choose an arbitrary location here, right? At this location, let's say this is the y. This is y. Okay, how much force do you have there? Should be that stress there times that small area there. So that's why you have sigma x times, actually I can write here, sigma x times the dA. That gives you the force there. Now how you calculate the moment of this force? So times the distance, right? Arm times the, okay, so you times y. That gives you the moment of this force, local force here, generate to the point O, or to the neutral axis point, right? So that is exactly this equation here. That's how you calculate moment, right? Any question about this part? That's the definition, how you calculate moment, right? Force times the distance. Okay, force is the stress times that small area. All right, with this, next part will be easy. Take this equation here. We know the stress. So you plug in, change the sigma x, and then you put it here, right? Plug in, combine the terms, and then you throw the E and the rho out. What's left in the middle will be, the integral will be only y squared. Now, why can you throw E and the rho out? E is a constant, material constant, so you can throw out the integral. What about rho? On this cross-section, we talk about the neutral axis. Rho is a constant, right? So it doesn't depend on y. We all talk about neutral axis. The rho of the neutral axis, that's a given value. So you can throw it out. So what's left here? Now, we call this y squared dA, I. I can define it, right? Actually, we already defined it a long time ago in statics. We call this one, what do we call it? Anyone recall? Moment inertia, right? It's similar to polar moment inertia. We talked about it earlier. Remember what's polar moment inertia in chapter 3? It's the rho squared dA, right? Everything to the center. That's why I call polar. To the center. Now you to an axis, to the neutral axis. So it's a moment inertia, right? Okay, how to calculate, we'll leave it later, but this is a quantity that depends on geometry, called moment inertia, right? So we just use what I here. Okay, once we define this I, so this equation become what? M equals to E rho, this one we call I. Now you get this equation. Okay, where's the negative sign go? Where does the negative sign go? Why does the negative sign disappear somewhere? Because see here, sigma is there is a negative sign here. There's a negative sign here. So they cancel out. Right? So I'm not forgetting it, it's just they cancel out. That's why they disappear. All right? Okay, so in summary, now we have this equation. That says the curvature of the generated by the bending. Okay, why we say curvature? It's 1 over rho, 1 over radius curvature. That's called curvature, right? So 1 over rho equal to the m over EI. So if you know how much movement you apply, then I can calculate how much curvature, how much bending you generate. What's the radius of curvature of that beam generated by the moment m? It's given by this equation. Right? Okay, so put this in your note and temporarily put aside. We're actually going to use this equation again for chapter 9. But here, let's move on. Okay, now we find out the 1 over rho. Okay, so can we find out the stress? Yes, I can take it 1 over rho back into here. So I'll get this equation. So I think it's right here. All right, so this is the equation. All right, because sigma, remember sigma equals to negative E y over rho. So now 1 over rho is equal to this. So take it in, that gives you this equation. All right. So this equation, stress is moment, bending moment times y, and then divided by the I. That's a moment inertia. So it's mi over I, right? Mi over I, right? Happen to be that way. All right. Okay, so now how the stress distribute when the y changes? Same, right? Linear distribution. When the y is 0, that's a neutral axis, stress is 0. And y is maximum, somewhere here, the stress is maximum. So it's a linear distribution. And in the beam, must be one side tension, stretch it, one side compression. It's always, because you must have one side y is positive, one side y is negative. That's why stress must be positive one side, negative one side. When you add them together, it's actually 0, because there's n is equal to 0. Right. Okay, so we spent all this time basically just show you, based on the plane assumption, we can determine how much strain you generate at any location, and then multiply E, you get stress, and then based on the integral relation, you find the relation to M. So now you have the stress equals to this. Okay, so for solving homework problems, you don't need to go through this process. You just use this equation we show here. Okay. So with this equation, if I ask you in a beam, I know I apply this much moment, M I know. And then I can ask you for any point, what's the stress? Right? For this beam, I can ask you, what's the stress here? What's the stress here? What's the stress here? Or what's the stress here? Or here? Any point. I give you a y value, you should be able to find it. Okay. Now, what matters most is what's the maximum stress. Okay. Right? So what's the maximum? So the sigma maximum equal to M times Y maximum, and then over I. So if you bend the beam, right? If the beam is going to generate some crack, you bend it too hard. Where's the crack going to start? Where's the maximum stress? Either the top or the bottom. Never in the middle, not start in the middle. Right? In other words, if you bend something, right, this high stress either top or bottom. The middle, actually not much stress. So if you have limited material, right, you want to build a beam to hold the maximum load. Where you want to put your material? You want to put that at the bottom or the top? Right? You want to avoid middle, because if you put everything in the middle, they'll not carry much load, not much stress. Right? So therefore, you actually see the I-beam. So when they build a beam, like the rail, you see this kind of structure. Okay, why they build this way? Because they put most material top and bottom, you can resist it to bending. And you save material, because you can cut the material here, right? But save a lot of material, and without losing much of the capability. So that's why you see the I-beam used a lot and as a beam. Okay, so in a nutshell, this is the key equation from today, how to calculate stress. Right? So if you want to say easy, simple, it's really simple, just this one key equation. Any questions? No question? Okay, let's see if I have an example here. Actually, next slide, I'm showing you how to calculate the I. All right, so to calculate the I, we have the definition. That's y squared dA integral. Okay, and then for common shapes, we already have it. So the textbook already listed, or you can check in the engineering manual, they'll give you. Right. So for this class purpose, we'll just use only the three type of beams. rectangular, circular, or hollow. Actually, we have the first one, that's the I-beam. Okay. I-beam, hard to calculate. So I-beam, there is a table. Actually, you can search based on the dimensions. They will tell you what's the I value. Right, so you just search the table, give you that. So in the homeworks, there are only basically this 4 type of beams. Well, maybe occasionally you will see from other textbook, they will ask you triangle shape beam. Right? But that's, for us here, it's rare. We commonly use either rectangular, circular, or tube, right? Hollow tube, that's circular. And then you have the I-beam. Okay, so let's say if I can go back to this, this problem here. See if we can determine the stress. Go back to our original question here. Okay, let's say I have this beam, right? I know the moment M. Now, can you determine the stress? I know M, let's say M equals 20. I know the dimension, right? This beam, let's say the length is 10 meter long. And then this dimension, so the cross section, if I draw it here, it will be, let's say, 2 by 2 centimeter. So 2 centimeter by 2 centimeter. I know the cross section. Can you determine the stress, the maximum stress in this beam? Right, so this will be 2 by 2. I know the cross section, 2 by 2 centimeter. This will be Newton, M equal Newton, 20 Newton meter. Can we determine the maximum stress? So sigma, because of bending, right? So that's the bending maximum stress. Can we determine that? Yes, okay. So you are equal to, what's the equation? Anyone remember? My over I, right? So my, then the y should take the maximum. Then over I. Okay, M is known. Now what's y maximum?
1.
It's 1. Because the neutral axis will be for rectangular. Actually, this is a square. Will be right in the middle. So here's your neutral axis. So the maximum y is 1. So y maximum equals 1. This equals 1. Now what's the I? How do you calculate I for a rectangular beam? Okay, I guess you haven't remembered the equation yet, right? So the 1/12 BH cubic. What's B? B is the width. B is 10? No, 10 is the length. It's cross-section property, cross-section. So the B in this case is 2 centimeters. Okay, what's the edge? 2 centimeters as well. We have a square, right? In general, the H and B can be different. So you plug this value, all this value in, and then you calculate the maximum stress. Now, can everyone do this? Find out the maximum value? Yes, right? So this chapter actually, to me, it's much easier than last chapter because there's not much variation. You just follow the equation. We give you an equation, follow, find out the answer. Right? As long as you understand the concept, that's it. Okay, now let me ask you a question. Where this maximum stress is located? If we find out this maximum stress, where is it located on this beam? Which part? Here? Here? Or here? So point A, point B, or point C? Where? It's A and B. Because one is compression, same value, one is tension. So make no difference, right? Compression, tension, we treat as same. Okay, but for real material, in reality, which part is going to generate crack first?
B.
B, yes, because things are weaker when they under tension. They're a little bit stronger under compression. Right? So the crack will generate at first at B, but the maximum stress will be both A and B. Now what about this point E and point F? The same, also maximum, right? So the maximum stress actually are all this line here, all the top edge, everywhere same maximum stress. The reason is because because this M is the same everywhere, right? So therefore, everywhere you have this maximum stress. Now, what if you have a situation, the moment M? Let's say you have a beam. Okay, the movement is this way. So this is the M diagram. Now, where the stress will be maximum? Let's say we have a beam. You don't have this. You have a concentric force. That's the M look like, right? This is the M look like. Now, where is the maximum stress happening? At which location? You will be at here. Because this location, moment is maximum. So the stress here at this 2 point will be bigger than this 2 point, EF. So this will be DG. So DG will be bigger than EF because the moment there is bigger. So to find out the real maximum, you have to look through the moment diagram. Oh, here the moment is maximum. So the maximum stress will happen somewhere here on this cross section. Right? So you need to check cross section, where is the biggest? And then along the beam line, where is the biggest? Then pick the real biggest one of the biggest one. Right? Okay, so any questions? All right, no question, then just practice, do the homework. Okay, I'll see you next time.